Hi, welcome back. We're starting a new chapter here, a chapter on matrix inverses. I'm excited because we're finally in a position where we can actually solve systems of linear equations, and this is a kind of a big key thing that we've been building up to for this whole semester up to now. And so now we're going to get to see the payoff of like several pieces that we've introduced slowly over the last several chapters, kind of coming together in this piece. And so we're going to start by talking about the inverse of a matrix, and it turns out that matrices can have two. They can have a left or a right inverse. So let's dive right in and start talking about this. Okay, so let's start by recalling when we were talking about solving a system with just a real number equation. We talked about this one before, where we said, we have a times x equals b, where a and x and b are all just numbers, just real numbers, right? And we said, we're solving for x. X is going to be equal to b over a. In the case where a is non-zero, right? And the step that we take here, it's kind of, we do it without even really thinking about it necessarily. But what we're doing is we're multiplying both sides by the inverse of a, right? So there's sort of this intermediate step here where we say, 1 over a times a x is equal to 1 over a times b, right? Or if you prefer, you can make it an a inverse, like this. A inverse ax is equal to a inverse b, a to the negative first power, right? And in both cases, these things sort of cancel out to 1, right? Because a inverse times a is equal to 1. Okay, again, assuming that you can invert it. Okay, so now we're going to expand that idea, but we're going to talk about the inverse of a matrix. And for matrices, it turns out there can be, so the general idea here is we want to say, okay, let's say we have some matrix A. Actually, let me scooch. Let's go ahead and scooch this away so we can't see. Okay. If there exists some matrix X such that X times A is equal to I, the identity matrix, right? Then X is a left inverse of I, right? Of A, sorry. X is a left inverse of A. Because we're multiplying A on the left to get I, the identity, which is sort of like the one of matrices, right? And one thing to think about here is if A is m by n, as we usually want these things to be, that means the identity matrix is square, so it needs to be n by n, right? Which means that X needs to be n by m. Okay, that's left inverse here. Going the other way, if you have the case that a times x is equal to I, like this, right? That's the right inverse. This x over here is the right inverse, left inverse. And in a similar way, if you try and sort of work this out, we're going to say this has to be n by n. This one is going to have to be n by m. So it's the same shape as A transpose in either case. But the size of the identity matrix is different because now this identity matrix is m by m. Okay, and so unlike with real numbers where it doesn't matter, an inverse is just an inverse, a matrix could have a left inverse but no right inverse, or a right inverse but no left inverse. It could have both. It could even have neither. So let's start with looking at left inverses. Okay, so so if there's a left inverse, then we can do something very similar to what we were doing a second ago. So now let's say we have a times x equals b, right? And let's say that there exists some matrix, let's call it C, that's a left inverse of A. Okay. If C is left inverse of A and A times x equals B, then I can multiply both sides by C, just like I did with the real number case, and I end up with something that looks like C A x is equal to B, right? But then because of associativity here, that's the same as C times A times x equals B. Oh, sorry. This should be CB over here. So let me scooch this over a little bit. This should be C times B because I'm multiplying C by on both sides, right? I got distracted by thinking about the parentheses and how my C's look like parentheses. Okay, so now I get CAX is equal to CB, and CA we said is the identity matrix, so now we have IX is equal to C times B, right? And I times X is just X, so X is equal to C times B. Which is, you can sort of think about, this is very equivalent to saying, since, this is, I don't want to actually write this, but it's almost as if I had said X is equal to A inverse times B. I don't actually want to write that because it's not the inverse, it's the left inverse. And there isn't, as far as I know, any sort of like standard notation for that. So we're just sort of writing it as this other matrix C. But that's the idea here. And one thing to note is that if the matrix A has a left inverse, then its columns are going to be linearly independent, right? So, and we can show that by saying, by looking at AX equals 0. Right? Remember we said that if the columns of A are linearly independent, they don't depend on each other, then this system of equations, AX equals 0, is only going to have only the x equals 0 solution, the sort of standard homogeneous equation solution, right? So maybe I'll write something to that effect up here. So I want to say if A is linearly independent, then AX is equal to 0 if and only if x is equal to 0 vector, right? And so if there's a left inverse, then we can do the same trick we just did. AX is equal to 0. We're going to multiply both sides by C. We're going to say C AX is equal to C0. Of course, C0 is still just the 0 vector, and CA is the identity vector, so X is equal to 0, right? Therefore, any matrix that has a left inverse is definitely linearly independent. Has definitely linearly independent columns, and we'll see why that matters. We'll see why that matters a little bit later. But okay, all of that was left inverses. So now we're gonna kind of move all that aside. Maybe let's scooch out so we can kind of. Okay, so this whole thing this whole thing here was left, right? So now let's do right over here. Okay, so okay, so for right inverse, it's going to look very similar, but not quite, right? Because if I try to do the same thing that I did a second ago, I can't. It was easy for me to left multiply both sides by some matrix B, or some matrix C, sorry, because these are both quantities, and I could multiply them. I could multiply them on the left by both sides. But if C is a right inverse now, that same trick isn't going to work. I can't insert. I can't like insert it in. So if I try to do like, I can't do something where I say like ACX is equal to CB, right? Because multiplication is not commutative in matrix multiplication in general. So I can't just like move it from that outer left side into the middle here, right? So that's not going to work. But that's okay. We're actually fine. Because we're trying to solve for x. Well, let's just let x be equal to c times b, right? Then a times x is going to be equal to a times cb. Right? We're just substituting in, right? Which is equal to AC times B, which is equal to IB, which is equal to B. Thus, AX is equal to B, right? And so it sort of works either way in some sense. That C times B ends up being the solution, which again we can sort of think of, like I'm going to do like some air quotes over here, but we can sort of think of it as like A inverse times B. X is equal to A inverse times B, right? But we'll get the full matrix inverse in the next section, so we're not there yet. Almost. But that's the right inverse. And unlike the left inverse, it's not the case that this thing implies that the columns are linearly independent, and it's not the case that this is a unique solution. All we said is if x is equal to c times b, then ax is equal to b. That means that this is definitely a solution to this system. That's one. But we haven't said anything about the uniqueness of it, which is actually kind of the opposite of what we did the other time, where we said if there's a solution ax equals b, then x equals cb is that solution, right? Which this relates to the overdetermined underdetermined system thing, because if there's many solutions, then the system is likely to be underdetermined, and if there's one or no solutions, then it's overdetermined, and those correspond. The underdetermined system is the right inverse one, and so this one is the underdetermined. So right inverse, underdetermined, right, or square, and then left inverse is overdetermined or square. And one way you can kind of see how that plays out is to look at what happens if you take the transpose. So if you have some left inverse CA, right? So you have CA is equal to I, right? Then we can take the transpose of both sides, right? I transpose is just I. And then CA transpose, remember your transpose rules, is A transpose, C transpose, right, is equal to I, right? So that means that if C is a left inverse of A, then C transpose is a right inverse of A transpose, right? And if the columns of A are linearly independent, that means the rows of A transpose are linearly independent. And so it's going to turn out to be the case that left inverse has the columns being linearly independent. I'm trying to kind of abbreviate just because it takes a long time to write all these words. The left inverse, the columns are linearly independent, and it's square or overdetermined. Right? The right inverse is the other way. The rows are linearly independent, and and it's either square or under determined. Okay, so okay, so this is, just sort of our first getting our feet wet on the weird world of matrix inverses. And we kind of saw there can be a left or a right inverse here, right? And either way, we can use that inverse to try and solve for a system of linear equations. It's but the sort of details will end up looking a little different, and depending on how a system of equations is set up, it might have either a left or a right inverse, or both, or neither. And the both case is particularly interesting to us, and we're gonna cover that in the next section. Thanks for watching.